Hello to all my physics pals. Paul Lake here with another physics problem solved. Hope you're doing well. We're going to do an electric fields problem here. I call it the electric field on a hanging pith ball. We're going to use these concepts right here. The electric fields for point charges, and then free body diagrams and good old Newton's second law. So doing a little review of some mechanic concepts in this problem, always a good thing. And so let's read the problem. It says a pith ball with a charge of negative 8.71 newtons, or not Newton, nanocoulombs, and it has a mass of 1.42 grams, is hanging from a string with a length of 20 centimeters and an angle of 25.3 degrees as shown. What is the magnitude and direction of the electric field at the location of the pith ball? And B, determine the positive charge shown if it is located 25 centimeters away from the pith ball. So this is my pith ball, just a little piece of fluff. You put foil around it or something, and you deposit a charge on it. And it's being attracted to this positive charge, so it's being held up like that. So let's write down what's given. Okay, and so what's given here? Well, we got this pith ball. I'm going to call this Q1, and I'm going to call this Q2. I quite often do that. Just assign a variable that allows me, an easy variable allows me to distinguish between the two charges. And so let's say that Q1 is equal to negative 8.71 nanocoulombs. What does nano mean? It means 10 to the negative 9, okay? And then a mass of 1.42 kilograms. So that's the mass of this thing. And it's 1.42 grams, not kilograms. Well, that's 0.00142 kilograms. Might as well convert it. The length here of this string is 20 centimeters. And you can change that to meters. Okay, 0.200 meters. And then this angle, theta, is 25.3 degrees. Okay, cool. And, and the distance, we'll call this R, right? The distance between these two, we'll call that R. And R is 25 centimeters. 25 centimeters, which is 0.25 meters, a fourth of a meter. Okay. And then what are we trying to find? Well, for part A, I want to know what is the electric field at Q1. So Q1 is almost going to act like my test charge. And then what is B? Determine the positive charge as shown if it's, the positive, okay, so Q2. Okay. Now, what I highly recommend, after you set up the problem like this, pause the video right now and try to solve this problem yourself. And then hit play and compare your work with mine. That's a good way to do it. All right, let's solve this problem now. Okay. So I want to find this electric field at this. Now, what do I know about electric fields? Well, electric fields, here's the thing you need to know about them is that the electric field is equal to the electric force that is experienced by a charge at a specific location in space. And in this case, it's Q1. Now, you may have seen this written in your textbook or in your lectures or whatever, as the electric field is the electric force divided by Q naught, or, Q, sometimes a Q sub 0, which we call a test charge. Now, in this problem, the pith ball is kind of acting as if it is a test charge. We're testing what the field is due to this. This is my source of electric field, and this is the charge I'm using to measure the electric field with. So this is a source, and this is the test charge. All right. So now I know what Q1 is, but now I need to know what this electric force is. Okay. So, well, what I'm going to do then is draw a free body diagram of this guy, because I need to find forces, and I got gravity pulling it, I got tension force, all that kind of stuff. So here's my pith ball, and we've got gravity pulling it down, and we have this tension force pulling it up like this. Now, why is it kind of not hanging straight down? Is because this electric field is attracting it. We have an electric force. Okay, there's my electric force. Now I'm going to make, let's make this my positive x direction and this my positive y direction. Now notice that this tension force can be broken up into two components, a vertical component plus its horizontal component. But where is this angle theta? Theta is right here, down here. So here's the y component of this tension force is equal to the tension force times the, now, should I use sine or cosine? Normally, when we want the y component of a vector, we use sine, right? But that's because we usually measure the angle from the horizontal, but we're measuring it from the vertical. So always use the right triangle. This is why it's so important to draw a picture of the problem. That I look at this and I go, oh, this vertical component is adjacent to the angle. And the way you find the adjacent leg of a right triangle is take the hypotenuse and multiply by the cosine of the angle, not sine. And the horizontal component, notice that it's the opposite leg of this right triangle right here. And the way you find the opposite leg is to take the hypotenuse times the sine of the angle. Very important idea of when to use sine and cosine. People always go, I don't know what. Look at the picture. Look at the right triangle. It'll tell you what to do, whether you use sine or cosine or tangent or whatever, by looking at the triangle. So now we're ready to apply Newton's second law. So I'll say, okay, let's sum the forces in the x direction. That equals ma in the x direction. So what's in the x direction? Well, I've got this electric force. That's what I'm trying to find. So that's good. And then minus, because it's to the left, this Ft, the tension force, times the sine of that angle. Okay. There are no other forces in the x direction. This component and this, that's it. What's the acceleration in this problem? There is none. This pith ball is in equilibrium. It's just hanging there. So the acceleration is 0, so that means these are equal to 0. So now I can solve, I say, hey, the electric force is just equal to the tension force in that string times the sine of the angle. Well, I know what the angle is, but I need to figure out what this tension force is. So let's sum the forces in the y direction. It's very common. You sum the forces in the x direction, you get a force equation. Sum the forces in the y direction, you get another force equation, and you can use the two together. So this is ma in the y direction. Newton's second law applied to the y direction. Now I look on my free body diagram. In the positive y direction, I have Ft cosine theta, and then minus the weight, mg, equals, once again, it's in equilibrium, so there's no acceleration. So this, now I can solve for Ft. Ft is equal to, well, I'm going to add mg and then divide by cosine theta. Woohoo! And now I can take this and plug it in here and get an expression for the electric force. So the electric force is going to be equal to Ft, which is mg, and then here we have sine theta Sine theta over cosine theta. Oh, well, that's just like mg tangent theta. So here's an expression for my electric force. So I can figure out what it is. Here's another way of doing it that's a little bit less work than this, but this only works in a special problem, like kind of like this one. This is an equilibrium. So when I add all three of these forces together, they have to equal 0. And so I can draw the vector addition. Here's the tension force. There's my tension force. And then I'm going to add to it my electric force. So pick it up, put it right there. So there's my electric force. And then here's my gravity force. And they all have, it has to make a triangle. You have to end up where you started. If you're going to add these vectors together and get 0, so remember when you add vectors together, you hook them up head to tail. First vector, second vector, third vector, you're back where you started. Okay. Well, here's my angle theta. And notice that tangent theta, the tangent of theta is equal to the opposite leg over the adjacent leg. And so now I can, here's another, I mean, this is just a different way of getting the same expression with a little bit less work. This is just mg tangent theta, okay? So that's a different way of getting it. Now, doing this only works if this turns out to be a right triangle. This technique works no matter what. This always works. So that's why I usually do it that way. All right. So let's plug in our values. The mass is 0.00142 kilograms. Or you could, put 1.42 times 10 to the negative 3 kilograms if you want. And then times g times the tangent of what angle? 25.3 degrees. All right, so that's Fe. So let's figure out what that is now. So that's 0.00142 times 9.81 times the tangent of 25.3 degrees equals. And I get 6. Wait a minute. Oh, I'm just checking my work, making sure I'm not messing this up. Yeah, 6 point, I got 6.58. Oh, that's interesting. Oh, okay. 6.58 times 10 to the negative 3 newtons. Okay. 0.142, did I do that right? I'm just checking. 9.81 tangent 25.3, is that the angle? Yeah, okay. So this is the electric force now. So now I can plug it in here to get the strength of the electric field. And so that's going to be 6.58 times 10 to the negative 3 newtons. And then I'm going to divide it by the charge that's right here. What is that charge? That's 8.71 nanocoulombs. Now, all I'm trying to do is figure out the magnitude of the electric field. So don't put the negative in there. That doesn't make sense. You just take the magnitude of the electric force divided by the magnitude of the charge, and you'll get the magnitude of the electric field. So E is equal to, let's see, divide by 8.71. Now, 8.71 nanocoulombs, so times 10 to the negative 9. equals. And we get 7.56 times 10 to the 5. So it's big. Newtons of force for every coulomb of charge. Okay, but they want magnitude and direction. Well, the direction of this you get by looking at the picture. Okay, so this is a negative charge. Now, this is a positive charge. So in this direction, it's creating an electric field that's to the left. But this is a negative charge, so it gets pulled to the right. Okay, so the electric field right here is to the left. Negative I hat. Now, what does negative I hat mean? Well, I hat means in the x direction. So negative I hat means in the negative x direction, and that's the electric field by this positive charge is moving to the left, but since it's interacting with the negative charge, that negative charge gets pushed to the right. So this is my answer to part A. Whew, not much room on this paper. Hope there's room for part B. And there is. Okay, let's do part B down here. Okay, so, hey, and by the way, if you find this helpful, please give it a like, share it with your friends, share it with your schoolmates. Hey, and subscribe to my channel. I've got lots and lots of physics problems, and I try to make I end up making about 4 or 5 of these a week. And in the comments, if you think I made a mistake, let me know. But if I made a mistake, can you put the timestamp on it, and then I can decide whether or not I'm going to remake the video or not. And if you just want to say hi or say thank you or whatever, my channel is small, so I respond to all comments. All right. So determine the positive. Okay, so we want to know what this charge is right here, what Q2 is. Well, remember that this is the source of the electric field. So the magnitude of the electric field is going to be equal to K times the charge of my source, not my test charge, but the charge of my source, which in this case, the source of the electric field is, so here's the electric field right here, but this is what's causing that electric field. So that's the charge you want to use, Q2, and that's what I'm trying to find, over R squared, R2 squared. And I just want the, yeah, so that's good. All right, so now let's solve for Q2. Q2 is equal to the magnitude of the electric field times R2 squared divided by the electric constant. Okay, so let's, so Q2, let's put our values in now. Well, we got the electric field at 7.56 times 10 to the 5 newtons per coulomb. We don't need to worry about that direction now. That R is given to be 25 centimeters or 0.25 meters, but we've got to square that, and then we have to divide by 8.99. This is the electric constant times 10 to the 9 Newton meter squared per coulomb squared. Now notice that I always put units in here because I use units to check my work. Newtons cancels newtons. I have a meter squared here. That'll cancel the meter squared there. I have a 1 over coulombs. I have a 1 over coulombs squared. So that will cancel with that. I have 1 over coulombs left over, and that makes coulombs, and that's what Q2 is measured in. So we are doing quite well. All right. So I got this 7.56 times 10 to the 5 times 0.25 squared equals, and then we're going to divide that by 8.99 times 10 to the 9, and I get 5.26 times 10 to the negative 6 coulombs. And there's my answer. You could also write it like this. And then 10 to the negative 6 is micro, so microcoulombs. You'll quite often see it written that way. Okay. If you did find this helpful, look in the description. I have links to other videos and lectures for this material. I'm also a private physics tutor, so if my rates are reasonable and I'm really good, and you know, I've got several clients now that I've gotten from my YouTube channel. So click on that link, and it has a way of getting a hold of me, and so get a hold of me. Yeah, and it'd be nice to meet you. All right. So anyway, hey, if you got all this far, I want to thank you for watching. I also want to thank you for being a physics student. Thank you for studying this. I know it's a grind. I know how hard it is. I know. Stick with it. Keep working. We need smart, hardworking people like you to learn this material, because you're the kind of person that keeps our civilization moving. We need technology. The device that you're using right now depends on people like you understanding how the fundamentals of electricity and magnetism work. So cool. So thank you. And until the next video, may the net force be with you always. That is all.